Here are some examples of writing reaction products from the second part of chapter 19. Originally, when I recorded this without sound, as it turns out, I wrote out the products as I talked. Since I now have the products written out, I think I will just talk about it. So with this first one, we have a ketone that's reacting with a peracid. And you can either write the peracid generically, or you could write MCPBA or use the structure of MCPBA. And the thing to remember here is you have these migratory aptitudes, which sort of kind of follow carbocation stability with two notable exceptions. One way to remember this is that the hydrogen migrates to give you a carboxylic acid from an aldehyde. But at any rate, what we have here is a primary group on this side, a phenyl on this side, and so you can see that phenyl migrates better than primary, so we end up inserting the oxygen to make the phenyl ester as opposed to the alkyl ester. And this, by the way, is a reaction that I have actually run using MCPBA. So in the second one, we have a sulfur nucleophile, which I put in the second half, even though it's kind of more similar to what happens with alcohols. So what happens with this dithiol is the same sort of thing that happens with an acid catalyst and diol. And so you're going to react the sulfur with the carbonyl and make a hemithioacetal. And then you'll ultimately end up with the thioacetal, and you have 1, 2, 3, 1, 2, 3 methylene groups between the two sulfurs. So this next one, we have a ketone that we're reducing with sodium borohydride. So this is essentially a review reaction. I added a little bit of a twist here because we have this methyl group with stereochemistry. And so what's going to happen is you're going to get roughly equal amounts, all other factors being equal, of the two configurations at the newly formed chiral carbon. But these are diastereomers, not enantiomers. So you have to be a little bit careful if you start with a chiral center in your molecule. So next we have two ketones. Sort of. We have an actual ketone, and we have a ketone that's been protected as an acetal. Don't ask me how they did that, but we have that. And so we're going to take this and we're going to react it with phenyl magnesium bromide, a Grignard, and then that will give us this intermediate, and protonation will protonate this. The reason we're using aqueous acid instead of just water is that will also hydrolyze off the acetal back to the ketone. I think this comes up later, but it does turn out, by the way, that you can protect an aldehyde specifically in the presence of a ketone, and that probably would have made a better problem for this, but I had the one from the book. All right, so here we have a two-step reaction. First, we're going to oxidize our secondary alcohol to a ketone, which gives us this. And then we're going to insert an oxygen on one side of this carbonyl, and it's going to be the tertiary side, not the primary side. And so we end up with this particular regioisomer. Cyclic esters have a special name. They're called lactones. And then F was the last of this series. We take a symmetrical ketone and a Wittig reagent that has 1, 2, 3 carbons, and kind of writing it while orienting the carbonyl compound the way it is, you get this structure. When I'm doing this reaction and several other reactions, I'm always really careful about counting my carbons because it's kind of easy to lose one or add one. So that's why I numbered this chain. That's actually not why I numbered the chain. So we can count 1, 2, 3, 4, 5, 6, 7, 8, and so we should have 6, 7, 8 carbons. The reason I numbered the chain was that I decided to beautify the structure of the final product and rewrite it that way. Either way would be acceptable on a test. And notice that by selecting a symmetrical ketone, I don't have any stereochemistry issues with this double bond. So the last question of two is asking which is the better way of these two different ways to prepare this particular compound. And I've specifically written the Z configuration product because normal Wittigs tend to give you almost exclusively Z, so I figured I'd write it that way. And so our choices are that we can take a primary alkyl halide and do this SN2 reaction to attach the phosphorus displaces the bromide, and then remove proton with butyl lithium and then add our ketone. Or we can take a secondary alkyl halide and do this SN2 to get an intermediate, and then add the butyl lithium and the aldehyde piece. And this top one is the better choice because of this first step where you're because you have a primary alkyl halide, which is a much more suitable SN2 substrate than a secondary alkyl halide.